You know the line, tea, Earl Grey, hot. I mean, for decades, that one simple command has been the absolute gold standard for science fiction. The ability to just make anything you want right out of thin air. It's this incredible dream of a world without limits, a post-scarcity future. Well, today, we're going to dig into how that dream is getting surprisingly close to reality.
Yeah, it's always felt like total fantasy, hasn't it? Something for, a few centuries from now. But what if I told you that two completely separate, super cutting-edge fields of research are now, for the first time, actually converging on a blueprint that looks a whole lot like a real-world replicator? The question is quickly changing from if we can do this to when.
Okay, so first things first. To build anything atom by atom, you hit a massive wall right away. Power. And we're talking about an almost unimaginable amount of energy. This is the big hurdle, the reason this tech has been stuck on the drawing board for so long. You can't just plug a replicator into a wall socket. You need a completely new kind of energy source. And that new source might, unbelievably, come from the vacuum of space itself. There's this theory called zero-point energy, which basically says that empty space isn't empty at all. It's this chaotic sea of energy always fluctuating. Think of it less like a quiet void and more like a raging river. The problem for scientists for decades has been, okay, the river's there, but how on earth do you build a water wheel to actually harness its power? Now you have to understand, this idea has been controversial, to say the least. Skeptics argue that zero-point energy is, by its very definition, the lowest energy state possible. So trying to get power out of it, they say, is like trying to make water fall from the bottom of the ocean. It just breaks the laws of physics. But the believers point to something real, something we can actually measure, called the Casimir effect. It's a proven force in a vacuum. And they argue it's not about breaking physics, it's about engineering a way to make that force we already know exists flow.
And that whole debate just got a massive jolt of energy. In March of 2026, a team led by Dr. Sonny published a major paper claiming that the weirdness of quantum mechanics might just be a natural side effect of space itself acting like a fluid. This isn't just theory anymore either. Their company just got accepted into a top accelerator program at MIT to build the actual hardware, a tiny chip they're calling a power chip.
And their first goal is super specific and tangible. One single chip, about the size of your pinky nail, that can produce a steady 1.5 volts. Now look, that is not going to power your house, but it could power an AirTag or a glucose monitor or some other small sensor, forever, with no battery. This is that crucial first step from a wild theory into a practical reality.
So, let's just imagine for a second they crack it. The power problem is solved. We have unlimited energy on tap. Awesome. You still have a second, equally gigantic problem to solve. How do you actually control all that energy with enough precision to arrange individual atoms into, a hot cup of tea?
For decades, the famous futurist Ray Kurzweil has been mapping this exact problem out. He's been predicting that by the late 2030s or early 2040s, we will have desktop machines that can build things atom by atom. And what's wild is that he's stuck to those dates for nearly 30 years, basically arguing that the exponential pace of tech, especially AI, makes it inevitable.
But here's always been the big stumbling block. How do you physically do that? You can't just build tiny little robot arms to grab atoms and move them around. The arms themselves would be made of atoms. They'd be way too big and clumsy. You need a totally different approach, something that can control matter without actually touching it. And this is where that second, totally separate field of research suddenly comes crashing into the story. The solution, it turns out, isn't mechanical at all, it's photonic. It uses light. Researchers are working on a new technique called the quantum walk, where they use photons to create precise pathways that guide atoms, kind of like a microscopic tractor beam. What these researchers are doing is basically figuring out how to program with light. They're creating these intricate little roadways to tell matter exactly where to go. One expert put it perfectly. This research is creating the software for the hardware of the physical world. It's the instruction set we need to finally start building with atoms.
And this is the real breakthrough moment we're living in right now. Do you see it? For the first time ever, we have these two completely distinct, credible lines of research. One for the power and one for the control. And they are both maturing at the exact same time. It's incredible.
So let's break it down one more time. You've got Dr. White's power chip, that's your battery. It's pulling limitless energy right out of the vacuum. Then you've got the quantum walk research, and that's your operating system. It's the code that tells all that energy exactly how to arrange atoms. One is the engine, the other is the steering wheel. You absolutely 100% need both to make a replicator work.
So, the billion-dollar question is, how do these two timelines actually line up?
I mean, we've got a roadmap for the power and a roadmap for the control system. The truly amazing part is how neatly they seem to stack up. It's almost a perfect match. By 2026, we should have the first proof of concept, that little trickle of power. Then, through the 2030s, the tech scales up as they learn to stack these chips, hopefully getting enough juice to power something like a phone. And then you hit the 2040s, and that's when the power density is projected to be high enough to actually fuel the kind of molecular manufacturing Kurzweil has been talking about all along.
And what does this all mean for us, for the world? It means a future where the cost of a physical object is no longer tied to its raw materials or the factory that made it. The cost is simply in the digital design. You wouldn't buy a new car, you download the blueprint for one. This is quite literally the end of material scarcity as we know it.
So, there it is. We have a real path to the power source. We have a real path to the control system. The fundamental pieces are moving out of science fiction and into real-world labs with actual roadmaps. The blueprint for the replicator is slowly but surely coming into focus. The only question left is, are we ready for the world that comes after it's built?